This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Cases, or in most cases, what happens is you're given a biasing condition, and then for that biasing condition and particular frequency, you're giving the scattering parameters for that particular transistor. Right, and what we're going to do is we've gone through the process of actually saying, well, if we had a particular source and load reflection coefficient, what is the the input and output resulting power for that particular network or amplifier, which includes the transistor biasing network, which I've hidden, plus the input and output matching. All right, that's what we did. Then we went through a simple calculation which hid a lot of complexity, but nonetheless what I said is, let's assume that we're given this particular transistor, it has the following scattering parameters, which is essentially, hey, I've biased it some way, it's got the following scattering parameters, and what I'm asking you to work out is the transducer gain, available power gain, and the total gain. And what we had done in the previous lecture is had worked out the formulae for GT, GA, and GP in terms of scattering parameters and reflection coefficients. And specifically, what we did then was to talk about, given after we've determined these quantities, how can we then use it to determine the power available from the source, the input power, the power available from the network, and power available and the power that's delivered to the load. All right, assuming that the generator has a voltage of 10 volts and the generator source impedance is 50 ohms, right? And I've given you that example. The example was essentially, went through a few pages of laborious, not particularly exciting mathematics, or it was really just simple algebra, to be honest. But what I wanted to emphasize was that you should be able to add and multiply and manipulate phases. Is everything okay? Is there an issue? If I'm missing something or whatever, just let me know, right? So, okay, so we went through that whole process, and then we worked out, things like, for this particular transistor, the power that was delivered to the load, the available power to the network, and the like. Right. Now, I also briefly touched upon the concept of, well, even at low frequencies, when we're building any kind of amplifier, we have to be concerned about stability, right? And so I can't remember exactly who I asked, but anyway, it was a question of, if we got even a simple op amp, does it ever become unstable, right? And the answer, and this is even if we, for example, if we designed a very simple inverting amplifier using an op amp, the question was, does it become unstable, or can it become unstable, right? And then what I showed was specifically, how about if I add a large capacitor to the output of an op amp, an inverting op amp? What happens? And that was the question that I presented or put forward to the class. And I asked for people to look at it. And essentially what I wanted you to do is go home, look at, hey, when I'm designing a power amplifier, it's not only gain that's important. The other thing that we're going to start looking at is, depending on the type of amplifier and the amplifier structure, and in this particular case we're going to relate it all to in terms of scattering parameters, this system can be unstable, right? So if you put a large capacitor at the end of an op amp, what you'll find is it begins to oscillate, right? Anyway, so we've got the same issue here, especially with microwave or high-speed power amplifiers. And then what I wanted to also briefly asked was, what's the definition of stability, right? Because I know a lot of you have done control theory, and as a consequence, when people talk about stability, usually, at least in their mind, they think, oh, this system's are going to oscillate, or it's going to go to positive or negative infinity. Its amplitude, the output of this amplifier is going to go to positive or negative infinity. And the truth of the matter is, as we discussed yesterday, it's never going to go above, in the long term, above or below the positive and negative supply rail, right? So you should always think of that as you're usually bound between the positive and negative supply rail. Okay, and then just to be a little bit careful, sometimes you might have a little bit of inductance. You might go a little bit above the supply rail, but let's forget about that. But generally, it's about, you're bound between the supply rails, right? So an amplifier never goes to positive or negative infinity, right? It either goes to the one supply rail or the next, or it oscillates between the two supply rails. So the question was, well. The question that we're going to investigate today is, all right, so we know there is this concept of stability as far as power amplifiers are concerned. So let's talk a little bit about the definition of stability, and we'll define this concept of unconditional stable. And then what we'll do is determine some tests in order to test for stability, and then we'll also look at, what can there be situations, especially when we're talking about conditional stability, where we can restrict the inputs and the outputs so that the system is stable, right? So the important thing here, the important concept which you've probably never encountered before, is that a system may be unstable, but it may be unstable, or may be stable for a certain set of input and output loads, source and load impedances. Right? Does that make sense? Okay, good. So let's talk about unconditional stability. So the definition is, a network is said to be unconditional stable in a particular frequency range, and this is also important, right? Because here, especially in high frequency, there might be frequencies that it's stable and other frequencies which it's not stable, but then you've got to be a little bit careful here when you're actually doing design. But at least as far as this lecture is concerned, you can say, well, we're going to look at it at a particular frequency range, and we say that a system's unconditionally stable if the input and output reflection coefficients are less than 1 for all source and load reflection coefficients less than 1. What does that mean? So what does this actually all mean? It means that for any passive input or output load, the network is stable, so it doesn't oscillate. And that's what gamma S and gamma L is, right? So we're saying that these gamma S's and gamma L's lie within the Smith chart, right? Because if you had gain, gamma S can definitely be larger than 1, right? And again, re-emphasizing the fact that in this particular case, unconditional stability isn't, this doesn't apply to unconditional stability, but at least for conditional stability, this is something that is critically important. All right, and what we'll do next is talk a little bit about conditional stability, and essentially what I'm talking about in conditional stability is that that the system is potentially unstable. We're not saying that it is unstable, but when we do these tests, it can be potentially unstable, but that could be unstable for a limited range of passive source and load impedances. And that's what's important here, that when we're defining stability, we're not saying, usually when you do stability in your control systems courses, you either say, oh, it's got right-hand plane, zeros, done, unstable. what we're saying here is it's a little bit more delicate, right? In the sense that the system might be unstable, but there might also be loads, input and output load impedances, that it's still stable and enables us to be able to use it, right? So control theory was just yay or nay, stable or unstable. Here it's stable, all good, doesn't matter. Any load or source impedance, all good. Unstable or conditionally stable, hey, it could be unstable, but there might also be certain load or source impedances that it's still stable and we can actually use it. Right? That's the delicate bit of this, which is a little bit different to what you've probably learned in your control theory courses. Right, now you have used the K-test for stability in control theory, but it's called something else, and you know, I'm getting a little bit old and I can't remember. But for us, what we're going to do is we're going to define this concept of stability, and there's going to be this concept or this test called the K-test. And essentially, once we determine these values for the K-test, we know that a network is unconditionally stable if this quantity K, written in terms of the scattering parameters of this matrix, is greater than 1, and also the discriminant, which is S11 multiplied by S22 minus S12 multiplied by S21, is greater than 1. All right? So they both have to be greater than 1. My apologies. Okay. Now, so that's the test. And that we usually use, right, to test stability. Now, there's another test that people have that people commonly use, not as common as the K-test, is this concept of a mu test. And essentially, it is also written in terms of scattering parameters. But the only difference, the only advantage that this mu test has over the K-test is that you can determine this value mu, and you know that the system is unconditionally stable if mu is greater than 1, but you can also order systems. So you could say, oh, this system has a greater mu than this system, so therefore the one that has got a greater mu is more stable. Right? So therefore, what that means is you can give it larger perturbations and it will decay back to a steady state value. So the larger it is, the quicker it decays back to a steady state value. Right? So that's all that's saying. Now, I don't usually commonly use that. I usually use, how do you call it? I usually just use the K-test. A lot of design software like Cadence and the like, when you're doing determining stability for RF tests, usually uses the K-test for stability anyway. That's the most common one. So that's what I would recommend that you're familiar with, and always have it like as a rule of thumb. So knowing that this is what you need to be using. But it never hurts. You know, occasionally you might see this mu test and you might say, oh, I know what that means and what its potential advantages are. All right, so let's now go through an example. Okay. Suppose we're given a gas FET. All right. Does anyone know what a gas FET is? Yes. All right. Anyone other than your colleagues in the middle there? All right. So who knows what a CMOS FET is? Or MOSFET? All right. And a gas FET is, so CMOS, usually the reason why, you know, the MOSFET's usually made on silicon. It can be made on, you know, silicon germanium, but usually silicon. Gallium gas is just another material where people use in order to make high performance, high frequency transistors. It's great for making, things for radars or high power communication systems. But it consumes a lot. The transistors are usually larger and they also consume more power. And you also don't have complementary pairs like you do in CMOS. So you don't have the enhancement and depletion or NP type thing in order to be able to make complementary pairs. So therefore, it's almost like it would be almost like designing an NMOS. Anyway, for this particular device, you've got a gas FET, and I say it's biased in such a way that you're given the following, or you achieve the following S parameters at 2 gigahertz. And these are some values that we've got. All right, you can say I've got a transistor, I've biased it. These are the values, right? That's all that's happening here, right? I'm just using. You can almost say that I picked them out of wherever you want to say that I picked them from. These are some values, and I'm going to use them in order to work out, is this transistor conditionally and unconditionally stable? How would I test that? What do I do in order to work out if the system's conditionally or unconditionally stable? We talked about it like 2 minutes ago. We do what kind of test? We do a K-test. Perfect. All right. All right. So let's do a K-test. So we need to work out this determinant. So that's S11 multiplied by S22 minus S1, and we'll just have to do some algebra. When we complete the algebra, we find that this delta is 0.7 angle 83 degrees. Okay, what's the magnitude of this? Don't look at it that. The magnitude is 0.7. So what do we know? But that is already, I don't even have to work out the K. We've said that unless delta and K are greater than 1, the system's conditionally stable, right? So trouble already, it's less than 1. It means that it's conditionally stable. And likewise, if I work out K, I've got both delta less than 1, K less than 1, unstable. So therefore, we know for a fact that the system's not unconditionally stable. What does that mean? Yes?
It can eventually become stable with certain, without certain impedance.
Sure. I'll just say it a little bit differently. So we know that it's unconditionally stable. So therefore, what we need to do is, what it's saying to us is, we can't guarantee at this moment in time that for all load and source impedances that it won't be unstable. Right? So, but it can be, it could potentially be stable for certain load and source impedances. Right? So, depending on what our flexibility is, well, we could say, well, throw away the transistor and let's look at a different type, or we can bias it differently. Or what we're going to do now is maybe let's look at potentially what are the input and output impedances for which this transistor is stable, and let's work out the process to identify what all the load and source impedances are. Right? So that's what we're going to do now. What we said is, if we got, step 1, we work out the K, we're given a transistor, we work out that we do the K delta test, and K is greater than 1, delta is greater than 1, what happens then? We know it's unconditionally stable, then let's continue with the design. Bob's our uncle, right? We get a transistor, we fail the K delta test, what do? Do we stop? Well, we can, or we can say, well, look, there could potentially be load and source impedances for which this is stable, so let's continue now in order to work out the stability circles. And that's what we're going to do now. We're going to work out how to determine for a given transistor that is potentially unstable, or is not conditionally stable, which is not unconditionally stable, I should say, what are the potential load and source impedances for which it's stable? Okay. And the other question is, and I just need to clarify this. If I was asking you to draw me for a unconditionally stable transistor, all the impedances for which it's stable on a Smith chart, what would you draw? It's unconditionally stable. It's all the elements on the Smith chart, right? Because it's unconditionally stable. It's everything on the Smith chart is stable. All right? All right. Okay, so let's now go through the process of defining stability circles. Does anyone want to say in their own words what we're doing? Like, what, you know, why we're going through this process? I just feel, the last two lectures I'm not getting as much feedback. I mean, not getting, you know, so it's just worrying me. So I don't know, am I not explaining it properly? I'm not doing something? Yes?
We're just trying to figure out, even if we have an unstable, a normally unstable system, which load could connect to the system, like in which case the system can become stable.
It can be stable and we can still use it.
Yeah.
Right, that's what we're trying to do. Is that clear to everyone? Yes? All right, cool. Okay. All right. So why is everyone being so quiet compared to the previous lectures? No? All right. Okay, so we know, based on our definitions, that an amplifier is stable if gamma in, or the reflection coefficient in, is less than 1, and gamma out, or output reflection coefficient is less than 1, right? So what we do is here, we're going to go through some boring mathematics. Now, I don't need you to know this off by heart. What's more important is, you know, how to use this. But nonetheless, what I'm doing is going through the process of actually deriving it for you. And all I'm saying is, let's look at condition number A. We want this to be equal to, when we want to find out when is this equal to 1. So we do some rearrangement, and what we find is this quantity is equal to 1 when S11 minus delta, where delta is this determinant, gamma L equals 1 minus S22 gamma L. Now, if we square both sides and we complete the square, what we can actually show is this gamma L, or the reflection coefficient of the load, minus this constant value, the magnitude of that equals to some constant here, right? And essentially, what this represents is essentially a circle which is centered at this location and has radius of this, right? That's all essentially what we've done. We've actually gone through, rearranged. We've looked at this. We've said that it's stable when this is less than 1. So what we say is, let's find out when it's equal to 1. So therefore we can define a circle. We do some algebra and we rewrite it in the form of the circle. And essentially we've got that the load reflection coefficient minus its center is equal to some radius, right? So and the radius is given by this quantity here, right? And you can do exactly the same for the source, right? And you can go through and work out for which values is this quantity here, gamma out, exactly equal to 1, right? And I've said, well, it's equal to, that circle is centered around this point, CS, and it has the following radius. Now, we've determined, so far I've said that stability, the system is stable when these two values are strictly less than 1, right? What we've determined so far is the values for which this quantity is equal to 1. Right? So now what we need to do is we need to do a little bit extra in order to work out, are the regions of stability inside the circle or outside the circle, right, as it intersects with the Smith chart. Okay, so let's continue with that, and what we'll do is it'll start becoming a little bit more clear as we do some examples. Now that we've determined the circles, we have to work out which regions are stable and which ones are not, right? And so what we do is we do a little bit of a thought test, right? And we say, well, let's consider what happens to this reflection coefficient when the load is matched precisely to the characteristic impedance of the line driving that load. And we know for that particular case, we have a perfect match, right? And if we've got a perfect match, we know that gamma L equals to 0, and we know when we resubstitute gamma L equals to 0 into our equation for the input reflection coefficient, because gamma L equals to 0, because we said we've done a perfect match, what we're left with is gamma L equals to S11. Of the magnitude of gamma in is equal to S11. So what it says is essentially, if S11 is less than 1, that implies that the reflection coefficient is inside the region of stability, right? Because we know if S11 is less than 1, input reflection coefficient is also equal to S11, which is less than 1, and we know that that's the region of stability. So therefore, under those cases, if we've got S11 less than 1, the region of stability is everything outside that particular stability circle, right? And likewise, if S11 is greater than 1, what we have is the stable region is the region which the stability circle intersects with the Smith chart. Now, you can say to me, Stan, you've confused me. Why did you do this? There's a lot of confusion here. What's the purpose? Let me say, you can go through the mathematics, but what are the important concepts here? Right? Let me distill the important concepts. The important concept is, hey, I want to work out a stability circle. Right? What I've done, I've gone through the process, worked out my amplifier or my transistor, or the transistor that I'm going to build an amplifier with is conditionally stable. Now I've got to work out my stability circles. There are two cases I've got to consider. Case number 1, magnitude of S11 is less than 1. Right. For that case, what do I do? Well, for that case, the region that all the impedances of the region of stability are all of the Smith chart except for where that intersects with the stability circle. Does that make sense? I'm not saying it succinctly. Okay, S11 less than 1. Draw the stability circle. The region where it's stable is everywhere outside this stability circle and the region, and everything outside this region. Sorry, let me say. I'm not saying. I'm a bit lost for words. It's everywhere in the Smith chart except where the Smith chart intersects this circle. Does that make sense? All right, cool. That's for S11 whose magnitude is less than 1. Case number 2, magnitude of S11 is greater than 1. All right, what do we do there? Well, under those circumstances, the region of stability is, where this circle, the region where this circle intersects the Smith chart. So this is this region where you've got this, maybe if I write stability region equals Smith chart intersection stability circle. Right? So it's this region. Does that make sense? Okay, and this one it's Smith chart minus the intersection of Smith chart. Okay, so essentially, just to recap, we got a transistor. We work out that it's conditionally unstable, right? Because we've done the K test. We then work out the stability circles. In order to work out the stability circles, we work out the center and the radius of the load of the stability circle for the input impedances and for output impedances. We have to do two sets of stability circles. Depending on S11 being greater than 1 or less than 1 or greater than 1, the region of stability, that helps us determine which is the region of stability. We also have to do the same for S22. Same rules apply. Exactly the same rules. Perfect? Good. All right, let's do an example. All right. Let me try to get the class to tell me what to do here, right? You've got the notes, so this isn't really helping, but, me hiding this, but anyway, let me delude myself. All right, I've got effect. Okay, got scattering parameters. I've told that it's being biased a particular way. And I wanted to use this as an amplifier. What's the first thing I got to do? So I'm going to start pointing to people. You've actually got the notes, so you know what to do. What would we do? Person just in front of me. Just one step.
To those parameters, we calculate our G value of CL and R.
Not yet, not yet. We're going to work out, first we want to work out if it's going to be stable, right?
Yeah.
If it's going to be unconditionally stable. K and delta. Perfect. All right. If K, suppose in this case K was greater than 1, delta was greater than 1, what happens? It's stable. K is greater than 1, delta is greater than 1, stable. I made a mistake on this one, on this. I thought I corrected it somewhere. Page, sorry guys, yeah, page 6, remember I corrected this. Page 6, I made it, it should be both of them greater than 1. All right. Okay, suppose they're greater than 1, they're stable. Okay, let's calculate it. We find out that they're less than 1. What happens? Well, what does it mean? Rather than what happens, what does it mean? Conditionally stable. And, yes? Could be stable for certain inputs and outputs. Perfect. Excellent. All right. How do we determine, person in the blue, how do we determine which regions are stable and not stable? Yes. Okay, yeah. So what we want to do is we want to work out the stability circles, right? So the first thing is we want to work out the stability circles. So one step before what you're saying, so we're going to work out the stability circles, right? In order to work out the stability circles, we've got to work out where the center is and what their radius is, right? So we go through, and I've given you the calculations, and if you do some algebra, you work out where the center of the load impedances and the radius is. And I've written it here as 1.361 angle 47, and the radius is 0.5, and also for the center for the gamma S is at 1.132 angle 68, and its radius is 0.199. Now, we're going to what we look at is we know that S11 and S22 are both less than 1, so that means, as you said, they're going to be which region? Sorry? Yes, the first picture, which is
inside the Smith.
so everywhere inside the Smith chart and outside the stability circle. All right, good. All right, let's go through the process of doing a design. All right, so we're going to print this on our favorite Smith chart. We're going to take out a dangerous piece of equipment here. And what we're going to do is we want to draw on the Smith chart the center. So we said the center was 1.361 angle 47 and radius 0.50. So now let's look down here and find. I remember that my protractor didn't go far enough, but we have to find. Yeah, I remember. I couldn't. Yeah, this one doesn't go. So I would need a ruler. But essentially, what you do is you go down here. You look at 1.36, right? So you get it on your ruler. You go 1.36. The next thing is you've got to find angle 47. Now, the thing that's important here is if you look on the outside of the at this location of the Smith chart, it says angle of reflection coefficient in degrees. So what we're going to do is we're going to find where 47 degrees is, right? So we go 40, 42, 44, roughly 47's here. And we had worked out the distance. It was 1.36. So what we do is we go from there to 1.36, right, which is roughly there. So that's where my center is. Okay. Now I apologise because I didn't bring a ruler, but essentially what I'm doing is two things. I say 1.361. I find 1.361 down here, right? So that gives me the length. I find where 47 degrees is, which is the angle of the coefficient, reflection coefficient in degrees, and all I do is essentially do that, right? And that's where I've drawn the point. Neglect that point. That was me that had made an initial mistake. All right. Then I want a radius of 0.5. That one's a little bit easier because this works for me. This protractor's can measure out 0.5, so I can draw the radius. So essentially I do that, measure 0.5 down here, and if I had done it carefully, all I do is just, draw the circle. Right now, you can draw the complete circle, but remember, it's the only here we're only looking at the region at which it intersects with the Smith chart, right? That's why I'm only drawing this segment down here. Okay, so here, especially for gamma in, are all the impedances on the Smith chart for which this is unstable, right? The input impedances. All right, so you've got that done for you now. Now, let's do the same for gamma S. Right, so what do I have to do for gamma S? S22 is less than 1, so it's still the same thing. We said that the CS is what? Angle 68. So how do I angle minus 68? Ooh, you don't know. Is it positive 68 or minus 68? All right, so I've made a mistake then. Okay, so I've drawn it in the wrong region. Okay, so I failed the exam. Okay. All right, so it should be on the other side. If it's negative, if it's truly minus 68, it should be on the other side. All right. Okay, failed. All right. That's why you should, when you're lecturing, the best thing to do is just copy out of the book. You know, don't try to come up with the equations yourselves or the examples yourself, because you know what? You're going to make a mistake and then you're going to look stupid like I just did, right? But essentially what happens is you try to identify the location. What we need to do is to find the radius of 1.132. We find that 1.132, we measure it out down here. We said it's minus 68 degrees, provided I've made these calculations right. Right, and then what we do is, if that calculation is actually right, we have to find minus 68, so it's down here roughly. So we'll do, what you would do is do that with the angle, draw the point roughly about here, or roughly about here. And then, what did we say, the radius is roughly 0.2. All right. Now check that it's actually minus 68, just in case I've made a mistake there, guys, right? Because it could be, it is minus 68. Okay. Then, yeah, it should be down here. All right, what I'll do is I'll correct it for the lecture notes, and you break the pencil and you fail the exam anyway, and anyway. All right. Yeah, so you just draw the circle. Sorry, I broke the pencil also. And essentially it would be all these regions in here would then be the regions which are unstable. Okay? All right, cool. Let's now do one more example. All right. Okay, someone want to help me go through it? All right, what do I do? You know, step by step. K-test. Okay, perfect. Lo and behold, like every exam question, it's going to be your, very likely, the K-test is going to fail, right? So it's going to be not unconditionally stable. Otherwise, if it was conditionally stable, you would finish there, right? There wouldn't be anything more that you need to do, right? So it's unconditionally not unconditionally stable. What do we have to do next? Right, stability circle. So we have to work out what? CL, RL, CS, RS. Okay. So work it out, and hopefully you don't do the stupid things that I did, make a mistake. You go through, and since S11, it would have been nice if I chose a different example where S11 was greater than 1, but in this particular case, S11 is less than 1, so the stability region is outside this defined circle. Right, so therefore, how would we draw this? Can someone remind me? Okay, so we're going to draw these circles. What do I need to do?
Match the radius on
The last line, yep. And find the angle, yep, perfect. And then draw, and then work out the radius. Yeah, draw the circle, right? And which one's the region of instability?
That's one is outside the circle, inside the Smith chart.
Okay, inside the Smith chart, inside the circle, inside the Smith chart. Yep, we got that. That's the region. All right, good. And this one is, on that one, it's going to be that. So anything, so really any impedances here, the system's going to be stable, right? If it was input or output, it would be stable. Right? So now you know how to work out your input and output matching, so therefore you've got a stable system. Now, why, we've still got a couple of minutes, I'll just take one more minute. Why wouldn't you either, you know, build it, you know, your gamma S, or your why wouldn't you choose a source impedance here? Or your, yeah, it's still stable, but, yeah, you don't have much margin, yeah. So you want to add a little bit of margin, right? That's all that is, right? In a practical design, right? So when you grab a resistor, or you grab an inductor, the other thing that you'll realise is they're never, even though they say 1 millihenry plus or minus 10%, you know, resistance 101 ohms plus or minus 10% or 1% or 0.1%, depending on the type of resistor you've chosen, right? Anyway. All right, cool. So now you've worked out stability circles. So what we're going to do next on Friday is we're going to talk about working out gain circles, right? So what we're going to do is we're going to say, hey, we've now got our system that is stable or unconditionally stable. These are the regions in which it's stable. These are all the impedances that give me these gains. If I want this gain, where do I choose? What input and output impedances do I choose so that I achieve that and I still maintain stability? So that's what we'll do next Friday. And then what we'll do is also start talking about noise figures and how we can do minimize noise figure, get maximum gain, and make sure that it's stable, all simultaneously, and all using our favourite friend, the Smith chart. All right, cool. Enjoy. Yes? It's a good question. It's radius, so it's, I don't know.
But then how could you draw that like 0.5 on the graph if you don't know how long it is?
Yeah, but you look at it here, because it actually tells you the length.
You're gonna like
relative to
put
this.
your
Yeah.
Okay.
So, you make this because
No,
it should be the square.
and it should be a square. Okay, I've made another
Is there a
mistake. Probably has to be a square. Yeah,
Which page?
it must be.
6.
Okay, so let me correct that. Yep.
This one, right?
Yeah, it should be a square. Yeah.
And for the next page, you use a minus 3.
All right.
Okay.
Okay,
My second
I'll
question is-
correct that.
Yeah, my second question is like here for CLRL for the load,
Yes.
we see S11, right? And for this one we see S22. Is that?
Yep. Yep. I've written it the wrong way around.
Oh, okay.
All right. Yes.
Oh,
Yes.
that's
Yes. Yes.
confusing.
Yes. 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 Yeah. Yeah. As I said, copy from a book. Don't try to do it from memory. You know. Yes. You're right.
Okay. Thanks.
You just want to be clear, so physically, what's the actual behavior of the power amplifier when this is not stable? It's like we have an input wave and
No, but it's okay. When it's unstable, right? So what we said is it's potentially unstable, but it would be stable for certain loads. Now, are you asking me if I chose one of the loads where it's going to be unstable?
yeah.
I don't know. It could actually go. It could oscillate, or it could actually hit the rails.
So just just never be steady state, and the output is actually unpredictable, and also
No. What we'll do when we do oscillators, then we can actually start looking at it, because what you'll do in oscillators is you'll choose the input and output impedance, so therefore it oscillates with a known frequency.
yeah.
So what depending on where you choose it,
Yeah.
there's either stable,
Yeah.
right, which means
We have the oscillations, and that's what we want at a particular frequency.
that if it's unstable and you're choosing certain things, you can actually make it. But generally, what you do is you design it in such a way that it's that the output is A times the input,
Yeah.
right?
So if it's unstable, it means the output will be unpredictable, and we don't know what is stable.
Well, I don't want to say unpredictable, because it could be unstable and be an oscillator, and it's predictable.
Okay.
Right? That's why. That's what I'm trying to be.
Actually, we have the case to use it when it's unstable.
Yes, oscillator.
Okay.
You want to build an oscillator, right? So therefore, you want to modulate. You want to generate your signal. How do I log out? Yeah.
Okay. Yeah.
You see, that's what I'm trying to say. So it's nothing's ever always bad.
Yeah.
You know, so you need stability. You need instability. Otherwise, you would never be able to build an oscillator.
Okay.
Right? And you want an oscillator for certain circumstances. Right?
Yeah, and also I noticed because when gamma in is bigger than 1, it also affect the input.
Yes. Because they're interrelated. That's because you've got S12. If S12, if you've got a unilateral transistor, then it doesn't. All right, and that's what we're going to do when we're doing the gain. What we're going to do is we're going to assume that we've got a unilateral transistor. S12 is 0, and then what we're going to do is do all the calculations, work out the gain circles, and then say, oh, if it wasn't unilateral, how off are we? And then you'll say, 2%. For engineering purposes, all good.
Okay. Cool.
All right? No worries.